Okay, so let's start. So did you guys, yes, thanks. Did you guys try to do any of the problems? Okay, you did all the problems, right? Good. So today, okay, so okay, so we are going to talk about limit distributions of extremes, and so we'll just focus on the maximum, but you can do the same thing for minimum, and it's the same basically. So there's a symmetry between maximum and minimum, right? Okay, so let me just recap a little bit what I did towards the end of the last class. So we had this object x max, which is the maximum of this set of random variables which are IID, and it's drawn from the same distribution P of x, right? So we are interested in the distribution of the maximum, and we have defined this quantity Qn of x. That's the probability that this maximum is less than x. So this is the cumulative distribution of the maximum. And what we said is that for IID random variables, since these are all independent, you can write it as 1 minus x to infinity p x prime dx prime to the power n, right? So this is what we did. Now, so we ask this question that whether this object with some suitable rescaling, let's say you some scale x by some shift which depends on n plus some fluctuations times some random variable z. So this x is a random variable, so this is the distribution of x, okay? So if you scale this here, so there is a shift and then some typical fluctuations times this random variable z. So in the limit n going to infinity, whether it approaches some n independent form, right? Whether such a form exists. If this form exists, then this is called a limit distribution. Okay, so this is a limit cumulative distribution. Similarly, you will have a limiting PDF, which will be just df by dz. Okay, and then we say that okay, if such a limit has to exist, so this should be of order 1 over n, right? And then this is the same condition that if I take a n going to infinity, you multiply by n, you change x to a n plus b n z p x prime dx prime. So this should go to a function only depends on z.
Could it also not decay faster than 1 over n square?
No, then it will go like 1. It will be independent of z, right? It will say this will be something like some small number if you just call it epsilon, right? So then this is epsilon n, right? This the whole thing. Now if this has to become n independent, epsilon should go like 1 over n, right? If it is 1 by n squared, then in the limit n goes to 0, it will just become 0, right? So this should become like that. So it should become like that. So in that case, So what will happen, that limit n goes to infinity, your q of n, where x is an plus bn z, this becomes your f of z, and f of z is given by exponential of minus g of z, right? Because in that case, this is a small number, this is of 1 over n, so then you can take it to the exponent, and then in the limit n going to infinity, it just becomes this one, right? Is it okay? Okay. So now we have to find out what is this function g of z, right? So the plan of the talk is today to find out g of z or f of z for all possible function f of p of x. So p of x is a probability distribution, right? So this is integral of p of x over all x is 1 and it's positive, right? So I'm going to do two ways. So first way is basically we'll try to think of all possible functional form of p of x. So as we say that it only depends on the tail of p of x, right? So it doesn't depend on the full function p of x, only at the tail, because the maximum comes from the tail of this function. So we'll try to think of all possible tails and try to find what kind of g of z you get. Okay, this is the first part of the lecture. And in the second part of the lecture, I'll do it in a more systematic way, okay, and show that if there is a limiting function, if there's a limit distribution, what are the all possible classes of limit distribution, okay. So let's just do part 1 and we'll just try to find some examples and we'll try to convince ourselves that these are the all possible kind of examples, okay. So yesterday we have already done one example, right? So that example was p of x is exponential of minus x, right? So x is greater than 0. It doesn't matter actually, you can also have a on the negative side, but since it just comes from the positive side, so we'll just look at this one, right? Less than 0. So it doesn't really matter what is there on the negative side actually. So you remember what we got for this one? We have already calculated this one. So what we have to do this one, right? We have to just find this guy and suitably choose an and bn such that this whole object becomes something independent of n, right? So this one is of course very simple, because what we say that x to infinity p x prime dx prime, this is again exponential of minus x, right? X greater than 0. Then if you just put this one, it's very easy to see that this is n exponential of minus x, x is just an plus bn z. And now you see that if you just take an equal to log n and bn equal to 1, this log n, so it gives 1 over n, that n goes away, bn equal to 1, so it becomes exponential of minus z. So therefore, this is your g of z, so your f of z is exponential of minus z, right? Let me write down this function somewhere, maybe somewhere here. So we have found one function where f of z is exponential of minus z. That's just for one example. And if I look at the so this is the cumulative distribution of the scale variable. So I can also look at the probability density function, right? So which will be just the derivative of this object. So this will be, so this will give me f of z is exponential of minus z, first this guy and then the derivative of this one, so exponential of minus z, right? So this is one function. So whenever you find a function, you should plot it, right? Because otherwise, okay, it's something, okay, you don't have any idea how it looks. So how does this function look? So z goes from minus infinity to plus infinity. So how does this function look? So this is one function we found. If I just plot it as a function of z, f of z. So how does it look? Okay, there's something here. So if z is very large, so how does this function behave? So this function, when z goes to infinity, it becomes 1, right? Because exponential minus infinity becomes 0, so exponential of 0 becomes 1. So this term dominates on the right hand side. So it basically has a exponential tail. It just goes like exponential of minus z, the tail. Okay. So how does it behave on the negative side? For z negative, so z negative, this is a large number, this is also a large number, right? This is some exponential, some positive number, okay, this is large, but this is also exponential of some positive number. Which one is larger now? So this is like if you just think of exponential of something as some y, so it's like y exponential of minus y. So which one dominates? So this side, right? So this one actually decays much faster. Okay, so on this side, okay, so it's not very this thing, but okay, so this has a super exponential decay on this side, and this is an exponential decay on that other side. Okay, okay, this is just one example. So what is the next example you can think of? The similar form. What is the other functions you know of this exponential? I mean, you come across every day. Gaussian. Suppose I have a Gaussian function now. Let's say p of x. So this is example 1. This is example 2. Is exponential of minus x squared by 2 sigma square. Forget about sigma. Right? Because this, you can always rescale this variance to 1. So suppose you have this function. So now I have to find out this integral. So you all know what is that integral. So x to infinity px prime dx prime. What is this integral? All of you know what is a exponential integral of a Gaussian. Huh? Yeah, so this is the error, complementary error function, right? So this will be with half complementary error function of x by square root of 2. So where error function is defined by, complementary error function is defined by is 2 by square root of pi x to infinity e to the power minus x square by okay, y square. Right, so this is an error function. But I need this for large x, right? Because I say that, okay, this term should be of order 1 over n, and that actually comes from large x. So for large x, how does a complementary error function behave? Okay, x goes to infinity, of course, complementary error function goes to 0. So how does it go to 0? Okay, so this one, it's an exercise. Right? You can also, of course, look at some books of function, there's some mathematical function or this thing, and find out how does it behave. But you should know how does one actually find out these asymptotic forms, right? So given a function, how does one find out these asymptotic forms for large x? Okay, show that this guy goes like exponential of minus x square by square root of pi x. Okay, let me just plus, okay, let me just put this thing here. So that it goes like exponential of minus x square, so that this guy goes like this, times the first term goes like 1 by square root of pi times x plus some order of 1 over x cube. Right? So these are, so you see that this is the leading term for large x, and this is a sub-leading term, and so on. Okay? So this is an exercise, and it's actually not very difficult. How are you going to do? You have to do some integral by parts and see that whatever is remaining, it's a smaller term. Right? So this is how you find asymptotics of this kind of functions. Okay? So therefore, so okay, this is this one. So this one therefore goes like, let me just write it, 1 by square root of 2 pi x, what is this, e to the power minus x squared by 2 plus this higher order terms. Right, so this is how it goes. So therefore, if I want to find this criteria now, so what I have to do is that limit n goes to infinity, right? So this n, as we see that, okay, I can take it to the exponential with a log n. So this is something exponential, right? So first let me just write this term. This is exponential of x squared by 2. So x squared is, okay, minus x is an plus bn z whole square by 2. Okay. This one, let's again take it up. Okay. So that becomes minus log of, there's an n there. So n by square root of 2 pi an plus bn z. Okay. And then that's all. Right, so I've just put this thing here and I've taken up with this log. Right? Now I have to choose an and b in such a way that in the limit n goes to infinity, this becomes something independent of n. Okay, so how do you do it? Is it okay? Huh? That will be a plus log. That will be like a plus log. Okay, right, thank you. Yeah. So now you can choose A and B in such a way that this thing. So roughly you can see, okay, so what do? You just expand this thing and then compare the coefficients of z, coefficients of z square, and so on, right? Because it will have all the thing. So the coefficient of z to the power 0 should be equal to 0, right? Then you find out coefficients of z to the power 1, find out. So these two conditions will give you conditions on an and bn, right? You have only two constants, parameters, an and bn. So these two conditions is sufficient to give condition on an and bn. For example, what is the condition on an? So an comes from here, right? So this guy, what is the condition on an? It says an square is equal to an square by 2. That's the term which is independent of z. What is the term independent of z from there? Log of n by square root of 2 pi an. Right? So this equation determines an. Right? Because if you know how to expand this guy, it's like 1 over 1 plus x. Right? So you expand, you have all coefficients. So this will give you an an. Okay? So what is the coefficient of b of z to the power 1? Similarly, you can find it out from here. So this will tell you, roughly you can see that, okay, an goes like, so it says that an goes like, to the leading order, what is the an, how does an go? See, an goes like 2 log n. Is it clear? See, this is the, an is large, something, okay? So this is the leading term. Okay, this one you can just write it as a expand the log. This is a leading term. And then it will be subleading term because this is like log n now. Right? So these are the subleading terms. So in fact, you can find out subleading terms, like all the subleading terms one by one, basically. Right? So this is how an go. So you can also find out how bn behave, and you'll find that bn goes like 1 over square root of 2 log n times plus this higher order term. So the two leading order for large n, this is how bn behave. Okay. So please do the exercise. You just put it there, and it's just a simple exercise, right? You have to just expand this and find out the compare the listing. So this is how bn behaves. And given this an and bn, so you'll find out that all the other terms will come as a function of bn by an, and bn by an goes like 1 over log n. So these are like a small term, right? So in this limit n goes to infinity, all those terms go to 0. So therefore what you will have is basically the linear term. So what you will find is that g of z is equal to this exponential of minus z. Right? All the coefficients of all the higher order term will vanish. So therefore you again have the same form. It's not a different form. So we can repeat this calculation and say that, okay, let's look at the number 3, and we say that since it's just the tail of the distribution, so px goes like exponential of minus x to the power delta as x goes to infinity for large x. Okay. So I'm going to put these notes in the after that lecture. I think I'm still working on the notes. I'm going to give you the notes, And also some of the references, actually I have already put in the whatever the main outline page, so you can find these references. Okay. So suppose this is how p of x behave. So how does this integral behave? So to the leading order again, so look at this integral. How does this integral behave? To the leading order, this integral behave just like that function, right? So this is a subleading term which gave you this log correction. So these corrections give you the subleading terms, okay? To the leading order, so therefore this integral still behaves like exponential of minus x to the power delta, right, for large x. Okay. There will be some prefactors, some polynomial prefactors, okay, but those will be the subleading term. Okay, but we are just interested in the leading order behavior. Okay, so this behaves like that. So therefore, this one is, so what is this criteria? Now you have limit n goes to infinity exponential of minus an minus plus bnz to the power delta. So this one is coming from this one. There's this n which will just take it up, so minus log n. Okay, so this is what you will get, right? So there might be some subleading terms, so those are like that. So what it means that, okay, so this plus some subleading terms. Okay, so therefore you can see now that if you again want demand that the coefficients of z to the power 0 term should be 0. So then what is the coefficients of, so this one you can expand. So what is the expansion? An to the power delta, you can take it out, okay, 1 plus bn by an z to the power delta. This one you can expand, an to the power delta. So what is this expansion? 1 plus delta bn by an z plus z square term, right? Delta into delta minus 1 by 2 bn by an whole square z square and so on. So this is what is done. So now what is the coefficient of z to the power 0? An to the power delta, and that should be like log n. Okay, then you will not have any n dependent term there, right? So therefore you have to choose an such a way that, see, it's up to us how we choose an and bn, right? So we have to choose an such a way that so if we choose now an equal to log n to the power 1 over delta, right? Because an to the power delta is like log n. And what is bn? We have to choose the coefficient of this term should be independent of n. So therefore this is an to the power delta minus 1, that gives delta bn should be independent of n. I can just set it to 1, right? So now this gives me bn. So this says that, okay, bn is 1 over delta an to the power delta minus 1, but an itself is log n to the power 1 over delta, so 1 minus 1 over delta, right? So if you choose your bn like that, an like that, and what about the higher order terms. Higher order terms will be n to the power delta minus 2 bn, right? Or n to the power delta minus n bn, right? So these higher order terms, you will see that if you take n goes to infinity, those higher order term will go to 0. Okay, so then just check actually, you can just check that, okay, all these higher order terms. So therefore again you have a function which is g of z equal to exponential of minus z. So therefore you again have the same function. So what we have shown that if you take any kind of exponential tails, right, irrespective of what is the value of delta, any kind of exponential of tails, you always get the same function. The distribution, when you scale suitably, you always get the same function, right? The function is independent of delta, right? An and bn, of course, they depend on delta and this thing, but the function is independent of delta. So you always get the same function, okay? So this limit function is the same, okay? What are the other kinds of tails you can think of now? Power law, okay, some tails which decay slow. So this is the exponential tail, right? So you all know how exponential tail behave. Okay, so it's something depending on delta, these functions, okay, it will go something like that. Okay. So basically if you plot it in a log plot, you should see that it just goes down, right? If you plot in, suppose log and log scale, then you should see that, okay, at some point it just goes down, right? So it has a log plot, basically it has some cutoff, right? So what is the function? Decays slower than this kind of exponential. It's a power law. Is there something between power law and exponential? Yeah, tail. Is there any function you can think of between power law and exponential? Exponential of log, right? Power law. Huh? So which is power law only for, okay? So this is a good thing actually. Exponential of a log decays slower than exponential, which is a power law, but you can have exponential of a log of something, right? Suppose, how does this function behave now? Let me write down this thing. So this we all did. Suppose I look at this function, okay. Exponential of minus c log x to the power delta, right? So of course if delta equal to 1, so what is this function if delta equal to 1? It just goes like 1 by x to the power c, it's a power law, right? But if delta is not equal to 1, you cannot of course do that, right? And then it's not a power law. And this is a function which is between power law and exponential. How do you show? So for delta not equal to 1, so there are two exercises. Okay, so one exercise is to show that, so how do you show that some function is faster than power law? So what is the peculiarity about power law? So power law is something so that if I look at some moments, right, because power law is something like what? How does a power law go? So power law goes like 1 by some x to the power 1 plus alpha, right? So if I look at some moments, or if I just consider some integrals like something to infinity, some large number to infinity, some x to the power n, okay, just call it nu, px prime px dx. So this for some suitable nu, after some time, depending on this alpha, this is going to diverge, right? This is going to infinity for some nu. Okay. Now show that for this function, all moments are finite. So that means that it has a tail which is slower than power law. So it has a function which all moments exist, but they are very large. Okay, so maybe in practice you may not be able to distinguish. If you do a simulation for some short distance, you may not be able to distinguish. So it has a very large moments, but still finite. Okay, so if x delta equal to 2, it's called log normal distribution, basically with some mu or something. But this is a distribution which is slower than exponential and faster than power law. The first one to show that all moments of this kind of function exist. Okay, therefore it's slower than power law. So this is the exercise 1. Exercise 2 is to show that you again compute this object for this kind of tail and show that it still goes to that limiting form. Okay, so limiting form still remains same. Okay, so we need even slower function now, slower tail, and those slower tails are the power law tails. Okay, so now we are going to, I've even forgotten what the exercise number, so some exercise number. Okay, so now we are going to look at this. Delta should be bigger than 1. Yeah. 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 No. I'm saying that delta equal to 1 is the power law.
No, I know. But
See. Yeah. It.
Still is slow.
Yeah. Yeah. Okay. Yeah. And now we look at this function 1 over x to the power 1 plus alpha as x goes to infinity. So alpha can be anything here, not bounded between 0 and 2, like that last time we did, right? So alpha can be anything here. So how does, okay. So far what is the summary so far? Any function till power law gives the same functional form, limiting functional form, right? This is the summary so far. So for this one, what do you get? X to infinity, px prime, dx prime goes like, again if you don't worry about the prefactor, etc., so this goes like 1 over x to the power delta, right? Because the PDF is just the derivative of this one, so that goes like x to the power alpha, right? Because that PDF gives us one extra term. So therefore this criteria now, what does it say? That limit n goes to infinity, n times this guy, an plus bn z to the power alpha should be equal to z of z. Okay? So can you guess an and bn? It's up to you. You just choose a and bn so that it becomes something independent of n. You can choose an to be 0 and n to the power 1 over alpha. Very good. Right? So then this thing something becomes a function independent of z. And what is the function? 1 by z to the power alpha. You could have also chosen an to be equal to bn, both n to the power 1 over alpha, right? And so you could have chosen an equal to bn equal to n to the power 1 over alpha. It would have given you another function. What is that function? Yeah, but this is not a different function, right? Because it's just a shift in z, right? So you'll find in some books, they prefer to write it this way because they want to put all these all the extreme values in one form. They prefer to write it in this way, but it's just a shift. So what we are going to stick to is this form basically, okay? So there's nothing different, it's just a shift in the this thing, okay? So now we found another form of g of z, and which says that f of z is exponential of minus 1 over z to the power alpha, right? So here z goes from plus infinity to minus infinity, so here z belongs to minus infinity to plus infinity. So here z belongs to 0 to infinity, so it's only on the positive side. How does this function behave actually? Okay, let me just write also the f of z, which is the derivative of this. So what is the derivative? E to the power minus 1 by z to the power alpha, 1 plus alpha, is alpha here? Okay. So again one should plot, right? How does this function behave? Right? So let's try to plot this function. This is for z belongs to 0 to infinity, and how does this function behave? So how does this function behave for large z, very large z? For large z, what happened to this exponent? Z goes to infinity, it just goes to 1, right? So this is just this function, right? So it has a power law tail. So, okay, let me just. So power law tails are the tails which are tails decay slower than exponential. So it has a power law tail, slower than any exponential. But how does this function behave near z equal to 0? So which term is dominant near z equal to 0? This term or this term? What is this called, these kind of terms? So these are called essential singularities, right? So these are the functions which decays faster than any functions, okay? So it's in fact has a very slow rise, okay? So that all derivative of this kind of function is 0 at z equal to 0, okay? So you know that if you have a function whose first derivative is 0, how does it behave? So suppose I have a function whose first derivative is 0. What kind of function has first derivative 0 at z equal to 0? Just think of polynomial. What kind of polynomials have first derivative 0 at z equal to 0? Can you speak loudly? Huh? Z square, right? So it says z square has a first derivative 0 because first derivative is z and z equal to 0 is 0. So what kind of function has second derivative is 0? Z cube. So this is z square. So z cube will go something like that. At some point this is going to overtake this function at z equal to 1 or something, depending on what are the coefficients. Z to the power 4, it will go like that. So now if you have a function whose all derivative 0 at z equal to 0, so that should rise very slowly, right? So this is a function which rises very slowly. Okay, and then this goes up and its function becomes 1, but then this guy takes over basically, right? So this is a function something like that. Okay. And this guy goes like 1 by z to the power 1 plus alpha. So you have a different function now. Okay. So you have this all exponential, so you have a class where you have a power law tail, and you have a class which decays faster than power law tail. So you have two different functions. But these two classes, this power law and faster than power law, this divide is different when we consider the sum of random variables, right? Because there also we had a power law and we had something whose variance exists. So if you have a power law with alpha greater than 2, variance still exists, right? But it belongs to a different class. Can you guess why? In the case of sum, if you have a power law with alpha greater than 2, the sum limiting distribution of the sum is still Gaussian, right? Because the variance still exists. But here it goes to a different class. Why is it so? Alpha greater than 2. Because whenever the variance exists, the sum is dominated by the typical events. So typical events comes from the typical fluctuations which is near the variance. So that's why for the sum, you still have the Gaussian distribution for any tail which decays faster than 1 over z cube. But for the extreme, this event comes from the tail, not from the typical thing, right? So since it knows the tail, right? So it still remembers the tail. Basically, the behavior is still dominated by the tail. So it has a different class. So for all power law tails, you have a different class. So we have a class for all power law tails. We have a class for functions, for probability density functions which decays faster than power law. So we have now gone from the, okay, let's go from this side now, okay? Power law, faster than power law. Is there some other function which decays faster than this kind of exponential? Some tail which decays faster than exponential? So we have already considered one case yesterday. No, even simpler than that. 1 by 1 plus x square is power law, no? For large x. Some functions which decays faster than any exponential tail. What about this function? Okay, so what about this function? Let's look at this function. P of x is equal to 1 between 1 and 0. Is the tail faster than exponential or no? Because it just goes to 0 at a, so these are bounded functions, right? So if you take any bounded functions, of course they decay faster than all the exponential, right? So these are the functions that are bounded, okay? So if you have a bounded function again, so this one we have already computed yesterday, you remember the answer, but instead of that, just take a general case. Suppose the support of this probability density function is bounded by something, let's call it A, okay? So it doesn't matter on the negative side, so this is your P of x, it doesn't matter what happens on the tail on this side anyway, right? And assume that this guy goes, the behavior of this guy, okay, it need not go to 0, but let's say this behavior of this guy, P of x, goes like A minus x to the power beta minus 1, right? So if beta is greater than 1, it goes like that. If beta is less than 1, it goes like that, right? This can either go like that, or, so this is the case where beta is greater than 1, or you will have something A where if beta is less than 1, so this guy can even diverge, so beta is less than 1, and beta equal to 1 is just a uniform, right? So this is the case where so this is the case where beta equal to 1. Okay, so suppose it's given by this, right? So it's a class of bounded functions, and as we see that, where do you think that the maximum value will be? Because it's bounded, if you take larger and larger n, the event will basically come closer to the boundary, right? So what do you get for this thing now? Of course, now the upper limit is bounded by A, so what we will find is that, so x to A px dx goes like, that's just the integral of this function. So how does it go? X to A minus x beta minus 1 dx prime. So what is this? So this goes like beta, right? So there will be some prefactors. So you can put all these prefactors, and this will be basically prefactors will just change your an and bn, right? So now you have this limit, n goes to infinity, n times this guy. So a minus an z, sorry, an plus bn z to the power beta. So this should be some function only of z, right? So what do you find? You find that an equal to a. So does it make sense? Because what you are doing is, since this function, these variables are bounded, right? And you expect most of the variables should be near the boundary for large n, so you have actually shifted your origin to the boundary. So this is what you do. Then some fluctuations, this is what it gives. So what is Bn? Bn is 1 by n to the power 1 by beta. So what is g of z? Minus z to the power beta, right? So why is minus? What is the range of z now? It's negative, right? Because you have gone to the boundary and you are looking in the other direction, right? So therefore you have another class which comes from the third one, so which is basically f of z, which is given by exponential of minus z to the power beta. So where z is from minus infinity to 0, it's negative, okay? And what is the form of this one? This one is again the derivative of this guy. So beta minus z to the power beta minus 1 exponential of minus z to the power beta, right? So this is a function, okay, this between that, and then for this is, and for z greater than 0, this function becomes 1, right? Because because this is a cumulative distribution. So this is given by this for this, and fz is 1 for z greater than 1. Okay, so this one is, therefore this is where minus infinity to 0. Okay, again you can plot this function. Now this function will be on the negative side. Okay, so this function will now depend on beta. For example, if beta equal to 1, so how does this function behave? This exponential of this is a positive number, so it's an exponential tail, but this guy goes to 0, so it decays exponentially, right? So this guy basically decays exponentially. So this is the case beta equal to 1. So now if you have beta greater than 1, then this guy goes to 0. Initially this one dominates, so this goes to 0, so it becomes something like that. And then at some point this is something beta is greater than 1, so it should go down this one, right? So this goes like that, and then at some point basically this guy will go below this one, right? Okay. Okay, my drawing is not this thing, but this extends to minus infinity all the way. And then the third one, if this is a case where beta is greater than 1, and if beta is less than 1, if beta is less than 1, then it will start from minus infinity, go, and then at some point this guy should go above this one, but still goes to infinity, right? So these are stress exponential tails basically. So this is beta less than 1. Okay, so this is how this function behave. Okay, so basically we have found 3 classes, right? One is this kind of function, one is this kind of function, and one is this kind of function. Can you think of any other distributions? So you have to find out what kind of tail is there. Okay, so what kind of function you get? So you have to again go back there and find out where does it belong. So it's going to fall into this class again, right? So therefore you see that you can come up with one after another some this thing, and you have to find out. So it's this exercise gives you a feeling, okay, what kind of functions are there, but it doesn't say that are there any other functions? Can there be any other functions? Okay, so this is what I'm going to do now, the part 2 of this. Okay, so you can take your function, think of any functions you can think which, okay, I want to find out something which decays faster than exponential, and okay, how does it behave? Okay, exponential of minus exponential of z or something like that, right? So where does it go? Okay, so you'll find that actually it is going to go to that class with again some suitable an and bn, but that's not very convincing that okay, you are just finding everything and then okay, for each p you are just trying to find out something. So we are going to do more systematic way now and find out what are the all possible classes of functions you can get for limit distribution.
So here in the bounded case, we assume it is of the form A1 raised to something.
So now I suppose that actually there's an example exercise I was supposed to give. Okay.
So
No.
Even for different classes would fall in.
So suppose you take this. Okay. Take a Gaussian, half Gaussian to the boundary and cut it off at some a. Right? You can take any function you want and cut it off at some a. That's a Gaussian exponential. Right? Exponential of minus a minus x whole square for all x less than a, right? And then again compute what do you get, okay? So these are supposed to be exercise, but okay, I didn't give. Okay. So you'll find that again you'll find something with this thing. So in fact this you will find with beta equal to 1, right? Okay. So now let's go to a more systematic way. That's the part 2. So what is the meaning of a limit distribution? We said that okay, if you take system size to be very large n scale suitably, it always converges to that distribution, right? So, okay, let's call it now. Imagine that you have a very large sample and you have blocked into, let's say you have x1, x2, xm. Okay, let me just put a different notation. x11, x12, x1m. Okay. Let's call it n. x21, x22, x2n, xn1, xn2, xnn, right? So imagine that you have this whole set of random variables. Okay, so n can be finite. Okay, n need not be distinct. So but this n is quite large. So now you are interested to find out what is the maximum of this whole set, right? So you want to find out the maximum of this whole set. Q of n times n. Okay, so these are the number of variables, total number of variables, right? So this is the distribution that the maximum of this whole set is less than x. This is how we had defined, right? But I can actually individually look at these sets and find out their individual maximum. Okay, so let's call this maximum is some m1, this maximum is m2, and this maximum is mn, right? So this m small n, right? So n is finite. Okay, so you look at this one. The global maximum is also the maximum of these variables, right? So if the global maximum is less than x, each of this maximum also has to be less than x. So now in our notation, so what is the probability that the maximum of this is less than x? Q n, because there are n variables, this is the probability that this is less than x. This for this one. Then similarly for another one, there are n of them. So this to the power n. Right? Do you agree with this one? Because the maximum of the global maximum is also the maximum of these individual subsets. If the global maximum is less than x, so the individual maximum also should be less than x, right? And this is the probability that, so each of them is the probability that this maximum is less than x. There are n of them, so this is what it is. So this is the probability that maximum of n times n is less than x, and each of is the maximum of n variable is less than x. Okay. Now if there is a limit distribution exists, okay, so limit distribution exists, so then what we say is that limit n goes to infinity, q n n, some a n n plus b n n z, so this goes to some limiting function, right? If n is very large, this is how we define. But this is also true with this guy, right? If n is very large, the maximum of these guys also should go to a same limiting distribution, right? So it says that limit n goes to infinity, Qn, but now I have to choose this coefficient. These coefficients are not same, right, because it's a smaller subset. So it says that An plus Bnz is also should go to a limiting distribution. Right? So therefore, these limiting distributions are also stable distributions in the sense that you can think of this M1 with some suitable scaling drawn from this function f, right? Because this distribution of that M1 is given by this f with some suitable scaling, right? So when you draw your random variables from these limit distributions, then if you look at the maximum of that, it's also given by the same limit distribution. Right? It's similar to the stable distribution yesterday I talked about. So yesterday the stability is with respect to the addition. So when you pick up some random variables and add them, that belongs to the same stable distribution. So here stability is with respect to the maximum, right? So now what it says, therefore, this means that, okay, there are n variables I have drawn from this distribution, okay, with some scaling. So f z of n should be equal to, it should be given by the same function, right? But as you see that when like in case of addition, I have to rescale this. So even for the maximum, I have to rescale the variable. So this will be given by the same function, but with some rescaling. Let's call this rescaling Cnz plus dn. Okay. So this is the formula which must be satisfied by the limit distribution or all stable distribution of this random extreme value statistics. So if you can find the solution, all possible solutions of this equation, right, this functional equation, so you have all possible classes, right? So we have to solve this functional equation. So how do you solve this functional equation? Okay. So let's first consider a case where Cn is not equal to 1. Okay? So we're going to consider two cases where we'll solve separately for two cases, Cn is equal to 1 and Cn is not equal to 1, right? So if Cn is not equal to 1, these guys are basically equation of straight lines, right? The argument. Right? This argument, this is like some z equal to z, and this is some f y equal to z, and this is y equal to Cn z plus d. These are equation of straight line. If Cn is not equal to 1, they are going to meet at one point. Right? So what is the point they meet? That's the point, let's call it z star, which is Cn z star plus dn. So there will be one point where they are going to meet, and this point is given by dn by 1 minus Cn. So this is a point where they are going to meet. And if they meet at this point, this argument is same as that argument, because this is also z star, right? Only at that point. So therefore, I have an equation which says that at z star, f of z star to the power n is equal to f of z star, right? So these are all the case where Cn is not equal to 1, because if Cn is equal to 1, those two lines are parallel, they are never going to meet, right? These arguments for Cn equal to 1, these arguments are never going to be same. But for Cn all not equal to 1, they are going to meet somewhere. And this is this point z star, which is given by that. So what kind of function f of z is? It's positive, right? Bounded between 0 and 1. It's a real function between 0 and 1, right? it's also a non-degenerate function. At two values of z, it doesn't have same value, right? Because it's a monotonically increasing function of z star, except if you have some probability distribution where there's some separate when f of z doesn't agree. Okay, so for any continuous probability distribution, these are monotonically increasing function between 0 and 1. So what kind of solutions you can get for this function for real f between 0 and 1? Is the equation x to the power n equal to x. It's 0 and 1. So these are the only two possible solutions, right? So it says therefore that at z star, f of z star is either 0 or 1. So these are the only possible solutions. Now, so fz is a monotonically increasing function. So therefore, if at z star it's 1, so what should be the range of f of z? It's a monotonically increasing function. So now take two cases. Case 1, case A, f of z star is equal to 1. So you're plotting f as a function of, z, and there's some z star, and at that point it's 1, right? So that means it's going to be 1 afterwards, right? So it's going to be 1 afterwards, right? So if it is 1 afterwards means the probability is 0, probability density is 0, right? So that's like this case, no? It's 1 afterwards, so probability is 0. So it's just a range of f, therefore, is below z star, right? So in this case, z is, so range of z is less than equal to z star. So similarly, case B, f of z star is 0 at z star. So therefore it's 0 anyway for z less than z star. So range of z is, so range of z is greater than z star. Okay, so now you have this thing, and okay, so now also you see that this guys, this is a property of this function f, that function at f z star is 0 or 1. So therefore z star also must be independent of n. No, although I have solved this equation, this right hand side, although it's dn by 1 minus cn, this should be independent of n. Is it clear? Because it's a property of this function f of z star, right? It's some function, that function cannot depend on n, right? So therefore this side is independent of n, so you have some z star. So now if you have some fixed z star, you can define this function f of z or f prime or some g of whatever h of z by just a shift, right? So for any finite z star which is not independent, so you can just take it to be 0. And I'll just set it to be 0. So therefore, I'll just call this is 0 and this is 0. This is just a choice that you can do by just shifting a argument of this function f of z, right? Like we saw that there's this function 1 by z to the power alpha, or somebody calls it 1 by 1 plus z to the power alpha. It's just a shift in the argument, right? So this is what you can do. So therefore, we have two classes we found. The functions, one class is defined, we have to still find these functions. But one class we have found, so let's call this not case, but we call it class 1, class 2. These are given by this condition that this is the case. If this is the case, I have to solve this equation. If this is the case, I have to solve this equation, which is, it's like if it is 0, it's like setting the dn equal to 0, right? This is what I did. I just by hand set dn equal to 0. Otherwise, you can put some other. So this, what is the equation I have to solve? So dn equal to 0, so I have to solve this equation f of z to the power n is equal to f of cn z for both these classes. I have to solve this equation. The solution of this equation with these different boundary conditions should give me two different kind of functions. Right? It's the same equation, but two different boundary conditions. Right? So these boundary conditions are important. Right? You can solve the same diffusion equation, but with different boundary conditions, and you will get different solutions. Right? Similarly, you can solve the same functional equation, but with different boundary condition. You get different solutions. So this will give me two classes. What is the third class now? The third class is the class I have excluded. Okay. So what is that class? Is Cn equal to 1? That's the third class. So Cn equal to 1, the solution equation I have to solve, f of z to the power n is equal to f of z plus dn. Right? So now I have this, so I have to still solve these equations and find out this one. So let's solve this equation. So how do you solve this equation? Okay, this 1, 2, 3, I'm just putting it randomly somewhere, but okay. So let's solve this equation, first equation. Okay. Okay, let's take a log because it's something to the power n. So take a log. It gives me n log of f of z is equal to log of f of z plus dn. Take another log, but before taking another log, this f is between 0 and 1, so log of f is negative, right? Log of something. So I should multiply by -1 and then take a log, right? So then what do I get? It gives log of n plus log of minus log of f of z. This is equal to log of minus log of f of z plus dn. Right? This is what I have. So this is an equation of the form g of, the whole thing you just call it g, some function of some x plus, okay, let's call it z, some z plus d is equal to g of z plus some nu. Right? Is it this form? Nu is log of n, and this function you just call it g, and whatever the shift dn is d. Right? So this is of this form. Okay. So if this is of this form, so the function you are just plotting now. Okay. So for all values of z, so if you look at some z and z plus d, that function is given by the, whatever the function here is given by this plus some number, right? So something plus some number. So what kind of function is that? So this is d. One solution is of course. So what kind of function is this first? this one, first look at this one. It's either constant or periodic, but the periodic function, as I said, that since our f is a monotonically increasing function, it cannot be a periodic. So therefore, this g of z in this case should behave something like is of the form mz plus c, no? Y equal to mx plus c. If you plot there, you see mz plus d is equal to d plus c is equal to mz plus c. Oh no, yeah, this plus you have this nu. So it would give you, okay, c cancels, basically c is still unknown, but it will give you m in terms of d and nu, right? It says that md, mz cancel is equal to nu, so it says that m equal to nu by d. Okay? So this is the solution. So therefore this guy, so g of z is just f of z, so f log of minus log of f of z is equal to nu by d. Nu is log n by dn. Of course, you can still have this c plus c. Okay, this is what you have. So therefore, times z. Okay, so f of z is given by exponential of minus exponential of log n by dn z plus c. Okay, this is what you have. And now we want these functions to be n independent, right? Because this is a function on the left hand side, there is no n. So therefore, dn has to be equal to log n, right? So it says that dn is log n. C again you can just absorb in this z now, because we said that this is just a shift, right? So you can actually set c equal to 0. It's just a shift in the variable, right? You can just, so it just says therefore, okay, you see c you can just set it to 0. So it says that f of z is exponential of dn is minus log n, because when z goes to infinity, this should go to 1. When z goes to minus infinity, so you have to choose dn equal to this thing, because otherwise it's just the inverted function. So minus z. So you see that for this equation, that's the only solution. Right? That's the solution we got before, right? For cases which decays faster than power law. So now we have to solve this equation for the other two classes. Okay, let me just take. Okay, it's a similar way you will solve. First, of course, you are going to take this thing. Okay. So if you have this equation, you can show immediately that f mn of okay. So can I take 5 minutes and this thing, or do it tomorrow? I'll just maybe just quickly tell you. So this is, suppose you have something like Mn. This is, of course, from that equation is given by f of Cmn to the power z. I could have also done the m first and the n first. So this is also then given by C of Cm, Cn of z, right? First I look at this guy, that is Cmz, and then I do the n1. So therefore this says that Cmn is equal to Cm, Cn. This is what it says. Okay? Now assume that this C is an analytic function in this m and n, so that I can take derivative with respect to m and n, and then you can either take derivative with respect to m, so which gives, if you take a derivative with respect to n, then it's m c prime mn, this is equal to c prime m cn. If you take a derivative with respect to n, okay, this is equal to cm cn prime, and where then you can compare these two equations, right? Write it in a nicer way, and then you can show that m cm prime by cm, you just cmm, this is equal, so this is equal to this, and then you rearrange, this is equal to n cn prime by cn, and this has to be a constant, right? Because this side is a function of m, this side is a function of n, this has to be a constant, and that constant you just call it gamma. Right? But then you can solve this equation, right? This is some, so what is the solution? So this is basically, this is Cn prime by Cn is equal to gamma by n. So therefore Cn is equal to n to the power gamma, right? You can, okay, of course, have some proportionality constant, but as we see that those constant you can just absorb in the distinct variable, right? So this is the solution you have. So therefore you have to solve this equation with Cn f z to the power n is equal to f of n to the power gamma z. So this is the equation you have to solve. Okay? So again, right? So this coefficient, in fact, you can just set it to, okay, this actually this is 1 because C of 1 is just 1, because if you just have take one guy, then there's no Cn, because if you put it here 1, so this has to be equal to 1, right? So this is just 1. So now given this, we have to solve this equation, and this equation again you take a log f of z is equal to log of f of n to the power gamma z. Okay? So you've seen this kind of functions, right? Let me just write it in a slightly different way, which you might have seen. So if you have some function g of lambda z is equal to lambda to the power some mu g of z. So what kind of functions are these? These are homogeneous functions, and what kind of solutions these functions have? Just as something to the power alpha. So this is, you are supposed to, okay. If this is this, show that this function satisfies a differential equation which is dz by dz is minus k by z, zz is equal to 0. So homogeneous functions given this property show that it satisfies this differential equation. Basically, you can just take a derivative with respect to z and derivative with respect to lambda, and then see that it satisfies this differential equation. And the solution is basically given by Gz is some a z to the power k, right? So therefore, if you now write down in terms of this your whole function, so what you will find is that your f of z is given by exponential of a z to the power 1 over gamma. You just transform your lambda to your n to the power gamma basically. Right? So this is the solution you have. Now you still have to find a and b, but that you basically find from your boundary conditions which are given by there, right? One that at z star, which is 0, one function has to be 0 and another function has to be 1, right? So what are these boundary conditions? So if you have these boundary conditions, then it says that so class 2 f of 0 is 0. So if f of 0 is 0, then what kind of function you should have? See, if it is positive, then it's going to go to 0, so this is going to become 1. So therefore gamma should be negative, right? So it says that gamma should be less than 0, and if f of 0 equal to 1, it says that gamma should be equal to 0. Okay, so now this one basically, if you write gamma equal to minus 1 over alpha, it says that and a equal to 1, f of z is equal to exponential of minus 1 over z to the power alpha. So this gamma should be positive. You write gamma equal to 1 over beta, and this guy has to decay on the other side. So a is minus 1. So therefore, fz is exponential of minus z to the power beta, minus 1 to the power beta. Okay, so these are these other two forms we have shown before. So you see that there are only 3 possible solutions to this equation, and these are the therefore only 3 possible solutions for this extreme value statistics. Okay. So there are no more other classes. Okay. Yeah, sorry, I rushed it at the end, but okay. Yeah, I guess it's clear. Okay. I guess we already passed time for question. Yeah. Oh no, it's only 4 minutes.